In this video, we're going to extend what we know about the disk method, which are those solids of revolution, to now include things called washers. And when we use this word washer, referring to a flat metal washer used in like carpentry, like on a bolt, not like a washing machine. So I have a video that kind of is going to show us what we're doing in the washer method. So we're still going to have a shaded region, and we're still revolving it. However, the region is not completely touching the axis of rotation. And so you can kind of see here, this is going to end up being revolved here around the x-axis. So you can see this gap here. That's going to create an empty space or a hole in the middle of each of our cross sections, thus creating like a flat metal washer. So we can see here how we have this shape and we're revolving it. And you can kind of see what this 3D shape is looking like with that gap there in the middle. So if we were to cut out a cross section, it's going to have this washer look to it with that hole in the center. And just remember, we're making this super, super thin. So even though in this picture, this guy had a little bit of thickness, we're taking this slice as thin as we possibly can. So if we go back to our notes, we can see that now our cross section is, like I said, this metal washer. So it's just this outside piece, and this hole in the middle is empty. So when we use capital R and lowercase r, we're just referring to this smaller radius of that inside space and the outer radius, which is the radius of the entire circle. And again, because our cross section is circular, we are finding the area of just this shaded region. And so if we think back to geometry, we know that if we're finding the area of something with a piece missing, we're going to find the area of the whole thing, which is the area of the outside circle. So your radius is going to go clear from the edge all the way to the center. That's going to be that big R. And then we're going to take out this piece that we don't need, which is going to be the area of this smaller circle. And we're going to use just that little radius to subtract from the big one. And so what that's going to give us is the area of one of these. And then if we multiply by this really, really, really small width, or that really small change, that's going to turn this into kind of just a really, really small volume of a very thin cylinder. So when we look at this, we see that both of these have pi. And since pi is a constant, we can factor it out. And what we end up getting is pi times big R squared minus small r squared. And then our dx at the end, again, is because each of these cross sections has a really, really tiny thickness. And we're going to add all of these together. And so that's where this formula comes from. So the pi out front is because we're still revolving. This is going to give us the area of the larger circle, and this is going to take that hole out of the middle. So each one individually is squared because when I revolve it, I'm going to have that hole in the middle. Okay, so we're going to do some examples. We're not going to finish these, but when we see something like this, we're not going to have a picture in most cases. So you do need a little bit of a visual to figure out what we're doing. So if we were to graph y equals radical x, we're going to get a graph that looks like this. And if we were to graph x squared, we're going to get a graph that looks like this. So you can see that this is the region enclosed, and I'm revolving it around the x-axis. So it's going to end up coming around this x-axis. And I like to kind of give myself a reflection. I mentioned this before, just so that I could see what's going on. So you can kind of see my reflection is going to come down in this kind of shape. And it's going to kind of look, again, like this circular shape. So hopefully you can kind of get a visual as far as what that's going to look like. And if we were to look at one of these cross sections, we would see that it's going to be a washer because it's got this gap in the middle. And that may be helpful to kind of draw in just so that you can see what you're doing. So just remember the definition of a radius is that it has to hit the center of your circle, which is always going to be our axis of rotation. And it has to go all the way to the edge of that circle. So remember, we need to calculate the radius of this larger circle. My picture is not the greatest, but we can see that the radius of this outer circle goes all the way to the center, and the center is going to be that x-axis. So the bad part of my picture is this inner circle should probably be up a little bit higher. But so this radius is going to be the red function minus 0. or in this case, radical x minus 0. And that needs to be squared because together all of this is going to give the area of that entire circle. Now we need to take out the hole that's in the middle, which is just that little piece, and I'm going to I'll use red. The radius here is going to be wherever that gap begins and where it ends. And it's going to begin, again, my picture's not the best, it's going to begin on this quadratic function, and it's going to stop right in the center, which is that axis of rotation. So this quadratic function is going to be x squared. Technically, we're subtracting 0 because it's the x-axis. And then that also needs to be squared. And then to create that really thin cylinder, I need to multiply by some small change. And my very first circle is here at 0. And my last one is out here wherever they cross. So I do need to figure out what this point is. And it is going to be 1. We can set these equal to one another to find that value. And we are going to get that they cross at +1. Okay? So this is how we would set up the integral that would give us the volume of this solid. Okay? Our next one, again, is very similar. Here, again, a visual really helps. So we'll go this guy in blue. So this is an upside-down quadratic that crosses the x-axis at 8. And this guy is a right side up quadratic. We'll go red on this one. And so we're taking this, this shape and we're cutting it off at x equals -2 and at x equals 0. And if you set these equal to one another, you do see that this is the point -2, 4. So it does say that we're starting at -2. And we're finishing here at 0. So we're really only taking this shape and we're revolving it around the x-axis. So again, I like to create that reflection just to help me kind of see what's going on. And so my reflection here is going to look kind of like this. And you can see that my cross section is actually like a washer. Okay, so I need to find the volume of this by finding the area of a flat washer and then putting that dx at the end. So my biggest radius is the blue function, which is quadratic, minus that axis of rotation, which is 0. So I have -x squared plus 8. Technically, we're subtracting 0 because we're revolving it around the x-axis, which is the equation y equals 0. That needs to be squared. So this will give me the volume of the entire shape as if there was no gap in the middle. And now we're going to take out that gap. So we're going to subtract. And now this middle piece, I'll use green as the radius, is going to be the red function minus 0, is all this empty space. So the red function is x squared, and technically minus 0. And all that squared, when we put dx, that turns it into a flat cylinder. And finally, we are integrating from -2 to 0 because this very first circle starts out here at -2, and our last one cuts off here at 0. Finally, our last example, we have y equals x squared and y equals x cubed. So my graph for x squared is just going to be that parabola. They are equal when x equals 1. So our next one is going to be x cubed, which they are actually going to cross at 0 as well. So it's going to look kind of like this. So this is 1 and this is 0. And so this little sliver here, like this crescent moon shape, is what we're going to revolve again around the x-axis. So it's going to come down here and kind of look like that. Okay. So our cross section is going to be this washer that has an outside radius of the red function minus 0. So that gives me the area of the bigger circle. And I need to take out the area of the smaller circle. So my inner circle here is going to be from the green function to the center, which is x cubed minus 0. And all of that gives me area. So to turn it to volume, I have to multiply by that really small width. And this very first cross section occurs here when x equals 0. And my last one is going to be out here when x equals 1. And so again, this would be what I would integrate in order to find the volume.